Initially, when we started talking about equilibrium constants, we looked at this generic reaction of some number of A's plus some number of B's yields some number of D's plus some number of E's. And then we would write out the equilibrium constant for this, and we would say that it would look something like this. The concentration of D to its coefficient times the concentration of E to its coefficient all over the concentration of A to its coefficient and the concentration of B to its coefficient. And then we took this idea and we started to specify different types of reactions. We said, okay, well, there's a reaction that we look at the dissociation of water. We called that Kw. We looked at the dissociation of an acid. We called that Ka. And we also looked at the dissociation of a base. So we looked at Kb. So all of these are equilibrium constants. We just started to denote in the subscript what type of equilibrium constant it was. So now what we want to do is we want to reintroduce that idea of solubility, but instead of just qualitatively saying whether something dissolves or is soluble in something else, we are going to have a more quantitative measure of this. And this is going to be an extension of the solubility, but we're going to try to look at this in a numerical way. And so whenever we talk about solubility equilibria, what we're actually going to look at is KSP. So K stands for the equilibrium constant, and then SP here stands for the solubility product. So for our first example, we'll look at calcium fluoride. So if calcium fluoride were to dissolve, it would form the calcium ions and the fluoride ions. Notice that this is balanced. We have the correct charges. And so if I asked you to write out an equilibrium constant for this particular reaction, you would say, well, KSP, so we're going to use SP to denote that it's a solubility product, would be equal to, well, in the products we have our calcium ion, so the concentration of calcium 2+, times the fluoride ions, so times the concentration of the fluoride ion squared. So here I've given you some data at equilibrium. So we could actually calculate the solubility product constant for this. So we could plug into our equilibrium expression here. So for Ka2+, we would have 2.0 times 10 to the negative fourth. And then for fluoride concentration, we have 4.1 times 10 to the negative fourth. And then don't forget to square that. And then we would find that KSP for calcium fluoride is 3.4 times 10 to the negative 11th. And we're going to learn how to look at those KSP values to talk about the solubility of different compounds. So now what I'd like to do is I want to show you how we can use ice charts for these different solubility products and go about finding the equilibrium constant, which in this case is KSP, in the exact same way as what we have done previously. So the first thing we want to do is we want to predict the product. So we're going to look at calcium fluoride. So we'd have calcium fluoride, which is a solid, and that would dissociate to form the calcium ion, so Ca2+, plus the fluoride ion, 2F-. And for the majority of these problems, what we'll actually see is for our ice chart, keep in mind for the equilibrium constant, solids don't matter. So KSP here is equal to the concentration of calcium 2+ times the concentration of F- squared. For most of the problems, or at least the ones we start out with, the initial concentration is 0. We'll get to some problems where you have an initial concentration of an ion, and we'll see how that changes what we do. But for most of these, it's 0. And many times in textbooks, what we'll see is instead of using X, they actually use an S, but it's the exact same thing. So here, instead of plus X, they would say plus S. And instead of plus 2X, they would say plus 2S. At equilibrium, you have S and 2S. But if you want to use X's, that would be fine as well. I'll probably use S's throughout just because that tends to be the convention. But if you use plus X and used X here and then plus 2X, that's fine. That's just the convention that people usually follow. So what we would do here is we would plug in for KSP, and we'll see that there are some fairly common solubility products that we'll encounter throughout. So we'll plug in for Ca2+, we'll plug in an S, and then for F-, we'll plug in 2S, but then that is squared. So we would end up getting that KSP for calcium fluoride is 4S cubed. Okay, let's look at another example. So here we're looking at the dissociation of silver chromate. So you're going to have to try to keep in mind what ions that these will separate out into and then what their charges are. So here we have a solid. We have Ag2CrO4. And that will dissociate into 2 silver ions plus, that's not dichromate, it's just chromate, so CrO4 2-. And then if we were to set up our ice chart, again, solids don't occur in the equilibrium constants. So since we weren't given any initial concentrations, this would be 0. Then the change would be plus 2S here, plus S. At equilibrium, the concentrations would be 2S and S. So KSP for this silver chromate would actually be concentration of the silver 1 ion squared times the concentration of our chromate ion. So whenever we substitute in our equilibrium concentrations, we'd have 2S quantity squared times S. So KSP here would be equal to 4S cubed. And sometimes in these problems, what we'll see is the problems may ask for you to find the molar solubility. So the molar solubility is actually just equal to S. So sometimes we'll give you KSP and you might have to go through and solve for S, like in this expression over here. Sometimes you'll have an ice chart. It just depends on the information that's given in a problem. But you will be asked to find the molar solubility. So let's go ahead and try another example. So here we're going to look at magnesium fluoride. So magnesium fluoride dissociates to form magnesium 2+ ions and then 2 fluoride ions. So if we were to set up our ice chart, this is a solid, so that won't occur in our equilibrium expression. We have 0 here, and we'll have plus S plus 2S. So at equilibrium we'll have S and 2S. KSP, again, remember, it's just like any other equilibrium constants. It's product over reactants. So here we'll have the concentration of magnesium 2+ times the concentration of our fluoride ions squared. We'll plug in, so we'll have S times that quantity of 2S squared. That's a very common error, is to not square the entire 2S, just to square the S portion. And this is, again, 4S cubed, which is a fairly common expression that we'll see. So the questions now that we have our solubility product. So if magnesium 2+ increases, what happens to the solubility? Well, think back to Q's and K's, okay? If this thing is at equilibrium, and then we are increasing the concentration of this. So now, if we're increasing that, that means that Q is going to be greater than K, because we're increasing the concentration of a product. Which means, if Q is greater than K, the reaction is going to shift back towards the reactants. So that means the solubility decreases. So if we were to decrease this concentration, that means our Q value, our reaction quotient, will be less than our equilibrium constant. So the reaction is going to push towards the right. It's going to favor the products, which means it's going to become more soluble. So the solubility will increase. So you'll want to be able to think about Q's and K's. But this is just a really straightforward introduction to solubility products. Next time we'll look at some of the factors that can affect solubility, and also looking at how to combine solubility products with other equilibrium constants to find an overall equilibrium constant.